So for this lesson, we're going to talk about postulates and theorems. All that a postulate is a statement that's accepted as true without proof. So the first one is a reflexive property. What this is any quantity is equal to itself. So if you've got a triangle over here that's labeled as A, B, C, D, and E. If you notice, there happen to be two triangles. There's this little triangle up top, CDE, and then there's a bigger triangle that's CAB. And if you notice, these two separate triangles, they both share angle C. So what we would say is angle C is congruent to angle C, two separate triangles, two separate angles, but it happens to be itself. Therefore, it's reflexive. The symmetric property looks like this. If A equals B, then B equals A. So any equality may be expressed in either order. It doesn't matter what you have on the right or on the left. For example, if X equals 5, you could also say 5 equals X. That's the symmetric property. Substitution. You do this a lot with algebra. Sorry about that. So substitution, you do this a lot with algebra. And basically, you know that if you've got something equal to something else, if A is equal to B, then A or B may be replaced with the other in any expression. And what this also is saying too is that any quantity can be substituted for its equal. Seems kind of strange, but go back to what you know. If we were to tell you that we knew that X was equal to 3, then we were to say to you, well, then what is X plus 5 equal to? And then what you would do is you would substitute in what X is with the number 3, and you'd say, okay, well then 3 by substitution plus 5 equals 8. So by using substitution, you can find out an answer to a problem. These next two postulates, addition and subtraction, again, is used a lot with algebra. If you know that you've got two equal quantities on the left and on the right, A is the same as B, then you can take a third equal quantity, which is C, and by adding C to both sides, you still have equals. So equal quantities or segments or angles added to equal quantities, segments, or angles always will remain equal. Same thing with subtraction. If you have equal quantities to begin with, and then you take a third equal quantity and you subtract that equal quantity from equals, you still have equals. So equals minus by equals are still equal. Again, I wouldn't get so caught up in, I don't get this, I'm not sure what this means. When we start doing proofs, it'll make so much more sense. But you know how to add things to both sides of an equation to solve, or subtract things to both sides of an equation and solve. The next piece, if you have one and only one circle can be drawn with a given point as the center, and the length of any segment as your radius. So what we're saying here is if I were to pick some point and I were to call it P, and I wanted to draw a circle using point P as my center with a radius of 3 units. Here's my radius, it's going to be 3 units. Well, only one circle can be drawn with that radius of 3 about that center being P. This right here, here's your center point. Any line segment that goes from the center point to any point on the circle is called your radius. At a given point, there's one and only one perpendicular that can be drawn. So what's happening here is I've got this line here, line L, and I've got this point here right on this line. If I want to draw a line through that point, There's only one line that can be drawn that's going to be perpendicular to line L. This is the only line, and I'll call it M, I guess, that's going to be perpendicular to line L. If I wanted to have that line slant ever so slightly, I'm no longer perpendicular through that point to the line. So there's only one way to draw a line through a point and be perpendicular to the other line. From any 2 points, there is only one positive real number that is the length of the line segment joining those points. This is basically like absolute value. So if I have this being P and this being Q, and I have this on a number line, then I would have to say that the distance from P to Q, either way I count, 1, 2, 3, 4, 5 units, or if I go from Q to P, 1, 2, 3, 4, 5 units. So either way, PQ equals 5 units. So from any 2 points, when you talk about the distance between them, it's always going to be positive. The shortest distance between 2 points is the line segment that joins those 2 points. So if I want to get from point A to point B, the shortest distance would be along that straight line segment actually, because it doesn't go on forever. A line segment has one and only one midpoint. That should make a lot of sense too. If I've got this point being A, that endpoint, and that endpoint being B, if we tell you that line segment AB is 6 units, whatever that might be, well, there's only going to be one midpoint, and that's going to be halfway between A and B, or at 3, which means we'll call this, I guess, M. So right here, we know that this has to be 3 units, and this has to be 3 units. So there's only one midpoint. And then we could also write, if we wanted to, not AB, AM equals 3, and then MB equals 3. Only one way to cut something in half. Similar to that with the midpoint is talking about an angle. It's got one and only one angle bisector. So we're going to put an angle has one and only one bisector. If we have an angle here, we tell you that angle A happens to be 50 degrees. Whoops, the angle A is 50 degrees. Then the only way to create the angle bisector is to shoot some ray off of A and cut that angle into equal halves. I'm just going to call this angle 1 and angle 2, which means angle 1 is congruent to angle 2, and that's going to also be the measure of 25 degrees. Only one bisector. Adjacent angles. These are going to be two angles that have a common vertex and a common side, but no interior points in common. So what that means is if I start out with this one angle right here, ABC, if I want to make adjacent angles, I can shoot some ray off of B, and I'll put letter D on there, and now I have adjacent angles. That would be A, B, D, and angle D, B, C are adjacent. We didn't say that DB, or excuse me, ray BD was a bisector. We're just saying that these are adjacent angles. They share a common vertex and a common side, which happens to be common vertex, common side, and then we've got two separate angles, right? We've got the angle here sharing that yellow side, and we got the angle here sharing that yellow side. This stuff then goes back, I think, to I don't even remember what grade, but complementary angles. There are two angles. They could be adjacent, attached, or non-adjacent, not attached, but their sum has to be 90 degrees. So complementary angles equal to 90. These happen to be adjacent. They share a common side and a common vertex. How do I know they're complementary? Because I see a box in there, and I would say that angle 1 plus angle 2 equals 90. There's 1 and 2. These guys are non-adjacent. They don't have a common side. But if I know that this is 60 degrees and this is 30 degrees, these angles are complementary as well. Supplementaries could also be adjacent or non-adjacent. And what's different about these guys, supplementaries, is these guys add to 180, not to 90. So something like this, angle 1 and angle 2. These are adjacent angles, and they are also supplementary. Here, angle 1 and angle 2, I'm going to give them actual measures. These guys are non-adjacent, and they are also supplementary because they add to 180. Linear pair. These always have to be adjacent angles. And they're always going to add to 180. They're always going to be supplementary. A linear pair makes a line. A line is a straight angle. A straight angle is 180. So a linear pair have to be adjacent angles that add to 180. 60 degrees, 120 degrees. And then vertical angles. These are angles that are formed by two lines that intersect. So what happens here, we've got these two lines intersecting to form these four angles. Vertical angles are angles that are opposite one another. So like angle 2 and angle 4 are vertical, and angle 1 and angle 3 are vertical. And what you need to know is vertical angles are always congruent. So 2 and 4 have to be the same measure, whatever that is. And then 1 and 3 have to be the same measure, whatever they are, because again, if they're vertical, they have to be congruent. Here's the end of it. Theorems. So we did postulates, which are statements that are accepted as true, and then there are theorems that are statements that can be proven true by using postulates or other theorems. Don't get too hung up on the definitions of these. But these are just things that we're going to use pretty much pretty regularly when we talk about proofs. One of them, all right angles are congruent. Well, that makes sense. I've got a right angle in one triangle and a right angle in another. All right angles have to be congruent. All straight angles are congruent. So all straight angles are congruent. Complements of the same or congruent angles are congruent. So if I've got congruent angles, and then I want to talk about their complements, the things that make them add to 90, they're going to be congruent as well. That's this one. Similarly, supplements of congruent angles are congruent. We've talked about this one already. If two angles form a linear pair, then they have to be supplementary. And we just touched on this one as well. Vertical angles are always going to be congruent. Okay, so then you should be good to go for the homework.